In modern system design, an organizational pattern has emerged where engineers are frequently categorized into silos, working exclusively on front-end, back-end, or hardware. But the requirements for senior systems architecture have changed. Building robust applications now demands the ability to operate across the entire hardware-to-edge continuum. To see what this cross-domain capability looks like in practice, we can examine the professional output of Rahul Kuchwa. His work spans the entire stack, from computationally dense academic medical research to enterprise-scale, globally distributed cloud infrastructure. By deconstructing Kuchwa's specific implementations, we can map the architecture required to build real-time, globally scalable applications. We will assemble a hypothetical system from the ground up, starting at the point of data generation. Tracing this full stack reveals the technical connections required to move beyond isolated features toward a unified system. The foundational layer of any modern system relies on the generation and processing of complex data. We begin with Kuchwa's academic foundation at YCCE, where he co-authored research on a multi-stage generative adversarial network, or GAN. This research focused on segmenting these intricate vascular structures within retinal scans to help diagnose eye diseases. Generative adversarial networks are computationally heavy. Running them reliably requires robust data pipelines to handle the mathematical load. This level of intensive computational research forms the bottom tier of our architectural model. However, computational models are dependent on the data streams that feed them. To move from the model to the source of that data, we have to look at hardware integration. Moving from AI computation to the source of data brings us to the challenge of physical world ingestion via IoT sensors. This requires a hardware-to-cloud bridge, a central concept in Kuchwa's systems integration work. The engineering challenge here is the nature of the data, an unrelenting stream of telemetry and device states that never stops. This continuous flow must be ingested, queued, and processed efficiently without overwhelming the system's memory. By adding an IoT sensor node next to our neural network, we complete the hardware tier. This foundation of hardware and data processing provides the raw material for the rest of the stack. But capturing massive hardware telemetry creates a new problem. The application layer must now consume this data without exhausting available bandwidth. We move up the stack to the application and state layer, where data is served to dynamic front-end frameworks through a Node.js backend. The standard industry bottleneck for this transfer is the traditional REST API. REST APIs return rigid blocks of data, wasting bandwidth on unused information. Kuchwa addresses this using GraphQL as an optimized API filter. This lets clients request only specific nodes they need, forming the core of our middle tier. Removing this payload bloat is necessary for maintaining performance when handling heavy telemetry streams. While GraphQL optimizes what data is pulled, it does not address the timing of those data changes in real time. Modern applications often require bidirectional communication for live data streams or instant messaging. Standard HTTP polling is inefficient here. The client must constantly ask the server if there are updates, creating a repetitive loop of overhead. Kuchwa utilizes WebSockets to establish a persistent conduit between the server and the client. This connection allows data to flow continuously without the need to re-establish a connection for every single update. This is a requirement for achieving true low-latency synchronization between the client and the server. Adding this real-time capability completes our middle tier, application and state management. But even an optimized real-time ATI is still restricted by geographic distance and the speed of light. We reach the final layer of our architecture, the global distribution layer. A fast API is still limited if a user's request has to travel halfway across the globe to reach a single origin server. Edge computing solves this massive geographic bottleneck by intercepting all user requests at localized nodes positioned closest to the user. To manage this at an enterprise scale, Kuchwa designed a serverless global redirect engine. This system utilizes AWS CloudFront, Route 53, and S3 to intercept the traffic and process redirect logic instantly at the edge. By handling routing at the edge, the rest of the system is shielded from traffic spikes and remains stable. This architecture provides high-volume reliability and security without sacrificing speed. Moving logic to the edge decouples system performance from the physical location of the central server. We now see the complete three-tier diagram as a single interconnected unit. Data generates at the hardware layer, is queried in the middle, and instantly routed via edge locations at the top. Tracing this path from generation to distribution reveals one continuous lifecycle. Kochwa's work demonstrates that modern engineering cannot be effectively siloed into separate disciplines. The constraints of the hardware determine the design of the API, which in turn dictates the edge routing strategy. True systems architecture requires synthesizing academic-level computation, optimized state management, and edge-first cloud deployment to build modern global systems.